I'll show you the equations. You can write them down if you want to. They'll be on your formula sheet. I as a function of time. That's okay, that's what I'll do. Okay, this should look pretty familiar, right? Again, it's a decaying exponential. Actually, this is, well, the exponential is decay. Is this for the turning the current off or turning the current on? Somebody take a stand. Look at the parenthetical expression. As time goes on, what happens to the exponential? What does it go to? E to the minus large is basically what? 0, yes. So as time goes on, the exponential goes to 0, which means the parenthetical expression goes to what? 1. Right, so 1 times E over R is just E over R. So this is for turning the current on, right? Because after a long time, you don't get 0. You could formulate the one to get 0 if you wanted to for turning the current off. But the point is just so that you see the flavor of this equation, that it works really a lot like a capacitor. Now, in a capacitor, I had, let me erase this. I had something similar. Right? Let's look at the argument of the exponents. They're both decaying exponentials. I looked at this and I said, you know what? RC, I'm going to call tau, my time constant for the circuit. This turned out to be the characteristic time for the circuit. If you're using this in a timing circuit, this is what you would do. All right, this is how you would alter the time, is by altering the resistance in the capacitor. Well, over here, I'm assuming there's resistance in the circuit. I can do something similar, right? Let me formulate this as E over R, 1 minus E to the minus T over tau. I've got to have T over tau, by the way. If tau is going to be some sort of characteristic time, I've got to have it in the denominator. You might see why. Think units. I've got to have the units cancel. Arguments of exponentials have to be dimensionless. So the units have to cancel, which means tau still has to be in the denominator. But for that to be the case, to match this up, it looks like I've got tau as equal to L over R. Right? This is the characteristic time of an induction circuit. So now let me subscript the tau. Capacitor, inductor. Function's the exact same. So RC, we would say, is the capacitive time constant. L over R is the inductive time constant. Okay? Everything after that, if you have to do a problem with this, proceeds exactly the exact same way. And I'm just going to tell you, I don't assign a whole lot of stuff with this. I'm going to treat this basically conceptually, but you still need to see this stuff and see, you need to understand what's going on. Each of these circuits has a characteristic time, right? The capacitive time constant tells you, it gives you a benchmark to talk about how the current either goes to 0 or to full current based on the charges on the capacitor. The inductive time constant does the exact same thing for the current flowing because of the induction, the self-induction. So the same effect happens, or a similar effect happens, but for drastically different reasons, right? But it's behaving very, very similar. Any questions about this? Yeah?
So is the induction referring to like just the total current, or like coils within the current?
So the current flowing through the circuit has to be the same current flowing through the coils, right?
Yes.
So you got the answer to both of your questions is yes. Unless I misunderstood.
Is there like just for any circuit, like because it has to be a closed loop, right? It will have the induction, right? So it'll have the.
Okay, so correct me if I'm wrong. You're saying what if there's a circuit with an inductor? There's an induction through the circuit itself, and then there's an induction through the inductor. What are we talking about?
Yes. Yeah. What is that?
Yeah. So in that case, you would add up the inductions. We're not going to get into that. So basically, this stuff you're going to see in this class will have one inductor that is either a representative of the circuit or a component, or both, or 7 components. All of it we're already going to put that together for you. But yes, in general, you've got to take into account the induction for all the possible loops that are going on in this circuit, which could be quite complex. We're just not doing that this semester. Does that make sense?
Yeah. Yeah.
Okay. Other questions? It's a good question. All right. So let's start putting some components together. Let's have a circuit. You don't have to do this, but I'm going to erase a little part of it. I'll fill it back in this way. This is going to be called an LC circuit. Physicists are very creative, and so we see this, we're like, oh, LC circuit. We're not that creative, right? Or at least not with naming things. This is an LC circuit. Basically just contains an inductor and a capacitor. Now remember, if you just have a capacitor, like that's the only component you have, just like you still had an RC circuit, because the wires have resistance. If you just have a capacitor, you still have an LC circuit because it still forms a loop. Really, you're going to have an RLC circuit, but we'll deal with that in a second. Right now, just imagine that there's no resistance, and all I have is a capacitor that's charged and an inductor. Right? So we're starting out with our capacitor charged. Now I have a switch that's open. In other words, there's a leg of this thing that's open. No current will flow for now, but what happens when I close it? And I'm going to say, let's let this be the positive terminal, let's be the negative. So y'all tell me, what happens to the charges that are on the capacitor when I close that switch? They will flow. How will they flow? From where to where? Yeah, or at least the way we consider electricity to be working, we're going to have positive charges start jumping off the terminal here, flowing around through the inductor back to the negative side here. Now, I've told you there's no resistance. Therefore, you tell me, is there anything in this circuit that will take energy out of the circuit? Remember what resistance is our electrical analog of friction. What friction does to mechanical systems, resistance does to electrical systems. It takes the energy out, right? There's no resistance here. So this is a system for which we'll say the energy is conserved. Now, think about what's happening. As the charges start to come off the capacitor, the coil is going to induce an EMF that opposes that, but fails to stop it, right? Okay, fair enough. But it does give some opposition, right? Okay, fair enough. So the charges are leaking off, the coil's opposing it, but nobody really cares, everything's still happening, right? So you will eventually get to a point where the charge is completely leaked off. The capacitor is now discharged. Does the current stop? Maybe a better question is, will the coil allow the current to stop? Do you agree that that would be a change in flux? Yeah, nature doesn't like that. So, interestingly enough, the current does not stop because Just like nature induced a magnetic field in the current to stop the flow of current, but failed, she now induces she failed to do it completely, right? There was current did flow, but she tried to stop it, right? Now that it's discharged, the last charge has come off, nature still doesn't like change. Now you have a change that's kind of in the opposite direction. So nature now induces a field that attempts to keep the current going. So the roles are changing, but remember, she doesn't like an increase in flux, she doesn't like a decrease in flux. She just doesn't like change. And so, in point of fact, the current does not stop flowing. Nature induces a field here, which now, an EMF, which keeps the current flowing. So what's happening? Positive charges have come off this terminal, but now that it's discharged, nature keeps the current going. And so you start to charge it up, but the other way. So positive charges start depositing themselves here, negative charges start depositing themselves here. Which is this, they don't start depositing themselves, but if the positive charges are building up on the one side, negative charges will build up on the other side. And so, eventually, all the charge ends up on the left-hand plate, right? So, all the charge has flowed around the wire, all the charge that flowed off of the positive terminal flows around to the negative terminal. It doesn't happen in a steady current. Nature doesn't allow that, right? But all the charges will get to the negative side. So, or what was the negative side? So you now have a fully charged capacitor. It's just charged opposite polarity to the original situation. Well, you have a fully charged capacitor. Now what happens? It starts to discharge the other way. So now current flows this way, and the exact same thing happens again. The induction of the coil keeps the current flowing after the positive charge is now discharged. And it charges up oppositely. And then after that, it does the same thing. And so the charges just start doing this, back and forth, and back and forth, and back and forth, forever. I mean, not really forever, but in this idealized situation, that would actually occur forever. You have, in fact, an oscillation, right? What's an oscillation? Well, we'll get there. That's the next chapter. You're not wrong, but you're a couple steps ahead of me. An oscillation is just a cyclical motion, right? The classic example from 1600 was put a mass on a spring on a frictionless surface, pull it, and then let it go. What does it do? Back and forth, back and forth, back and forth. Oscillates back and forth, back and forth, back and forth. We had all sorts of equations to describe that, right? We're going to use those results to get some results here. But first of all, do you see what's happening and why it's happening? Nature hates change, right? Again, it's not a rule, it's just a guideline, but it works pretty well. Questions about this? Okay. Let's look at this from an energy standpoint. We're physicists, at least, or we're in a physics class. We always have to look at it from an energy standpoint. Recall this equation from a few weeks ago. This is the energy stored on a fully charged capacitor. 1/2 Q squared over C, where Q here is the full charge of the capacitor. Right? To make this more general, let me change this Q and change UC. Well, I'll rewrite it so you don't have to erase it. Right? If the charge is changing, and we saw situations where that would happen, then you can talk about the energy stored in the capacitor at any time, right? Energy is a function of time, as 1/2 Q, she squared. Q is a function of time squared over C. So the capacitance here is a That's just the characteristic of the component. This is a constant, but Q now is we're allowing Q to change. So at any point where some Q is on the capacitor, it has this much energy. I'm just going to give you the one for the inductor. There is energy stored in the inductor. Why is there energy stored in the inductor? Well, there's a magnetic field in the inductor. We saw that energy is stored in the electric field of the capacitor. Right? That's what we had a discussion. And I said some people don't agree with that terminology. Most physicists do. We're going to take that line here, that in the electric field in between the capacitor plates is where the energy is stored. Right? So the energy is stored in the field. Well, there's a magnetic field in the inductor. That's where we're going to store the magnetic energy. So there is a UL, energy stored in the inductor. 1/2. Make sure I get this right. This is one of those that I never have memorized. Yep. Li squared, which let me rewrite as a function of time. Sorry. Alright. This is the notational convention adopted by your book and many others. A steady or constant quantity will be written in uppercase. A changing quantity we're going to write in lowercase. So all I'm saying is if there's a steady current flowing through a coil, this is how much energy is stored in the magnetic field. But in this case, we're going to allow the current to change as a function of time. Therefore, the energy stored as a function of time. And we have lowercase I squared. So I have the energy stored on the capacitor at any time, the energy stored on the inductor at any time. Okay? Now, think back to what I asked you a while ago. Or what I said a while ago. No resistance means no energy escapes the system. Alright, take a step back in time with me to 1600. Mass on a frictionless surface attached to a spring with a spring constant K. Pull it back, let it go, it oscillates. If there's no friction, and by frictionless I mean the surface and the spring, this is our nice idealized Hooke's Law spring that never breaks down and never heats up, because that's how we roll. Nothing to bleed energy out of the system. Therefore, the energy at any point in time has to be expressible like this. 1/2 kx squared plus 1/2 mv squared, where x and v are both functions of time because the thing is moving and the speed is constantly changing, position is constantly changing. But all we're saying is that the total energy of the system is equal to whatever's in the spring plus whatever is kinetic, right? I can get really granular with this if I remember that x and v have a relationship, right? What is the relationship between position and speed, or position and velocity? Come on. What is the relationship between x and v? Thank you. Yeah. 1/2 k x squared plus 1/2 m dx dt squared. Right? That's all I did. We recognize that this is an oscillation, and through some, I'm not going to go through the whole process, but hopefully when I say that this has an oscillation frequency, I'm on that section of the board. Oscillates with as an oscillation frequency omega, which turns out to be root k over n. Right? This is old stuff. I don't know if your 1600 professors derived this for you. It takes a little bit of diff EQ, second order partial differential equations. It's not a prerequisite for this course. Some people derive it anyway, just so you can see it. Some people don't. So I don't know if your 1600 professor derived this or not. But at any rate, you have an equation. You have a partial derivative. No, this is a full derivative equation. I'm sorry, differential. You have a differential equation that yields a solution for an oscillation frequency of this. All right, go to this system. Something really similar is happening. What is the charge doing? Back and forth and back and forth. It's oscillating. Sum up the energy at any time. It's got to be the energy stored in the on the capacitor. I'm leaving off the time dependence, but these are functions of time. Plus the energy stored in an inductor. Right? Hopefully we're starting to see the similarities here. Okay, well, I've got a charge and a current. What is the relationship between charge and current? The answer is the same. Derivative. Yeah. This is the same problem, just with different symbols. It yields the same results, right? I have an oscillation frequency that we can talk about. Switching colors to metal. Oscillation frequency of 1 over root LC, or root 1 over LC if you want. There were further things we did with this, which I'm out of room. Let me see if I can write them up here. I'll write them here. We figured out that we could characterize this where A cosine omega t, and I'm going to give you the full one. Let me give you a better omega, plus phi. That is the position as a function of time. What is A? Amplitude. What's that? Maximum displacement from equilibrium. What is omega? Oscillation frequency. What's phi? Phase angle, the shift, right? This allows you to use either sine or cosine and start it at any position. If you chose to use a cosine, well, what this tells you is that you have to start your stopwatch at 0 in order to have this make sense. Because at 0, that's when you've moved it over and let it go. Your position should be A, right? But if you don't start your stopwatch at 0, that's not the answer you get. So the phase angle is just there to allow you to start your stopwatch whenever you want to, right? What's the difference between sine and cosine? Phase angle of pi, right? Cosine of 0 is 1, sine of 0 is 0. It's just a phase angle, right? So it just allows you to use the cosine without changing